functional analysis class. So today we are going to talk about the dual of a vector space, or the dual of a norm space, and also with topology. We might not start with, I might not tackle with topology in the current session, maybe in the next, but we'll see how far we will go. So if you recall what we discussed last time, because I mentioned this concept of dual topology. So if you recall, if you recall when we discussed about the space of bounded linear operator from the norm space X, the norm space Y. So X and Y are norm spaces. Otherwise, we cannot talk about continuous or boundedness of an operator. We talk about continuity, it means that there's already a topology in X and Y. And that topology, in fact, is the norm, right? So they are norm spaces. So if I can call the operator T. So this is the space. And in this space, we saw that we can define a norm, which is the operator norm, right? In this space. And we saw that if Y is a Banach space, the entire space itself is a Banach space. And in the particular case of Y equal to R, we know that R is a Banach space. So the given space, that is, for Y equal to R, X star will be the set or the space of bounded linear operator from the norm space X to the norm space R. So each time we fix Y to R, which is a Banach space, X star is what we call the dual of X. Now you see that R is fixed, right? R is fixed, we know R is fixed. What we will change here is the X, right? Instead of writing all this, we just call it X star. That's what we call the dual of X, the dual of X. So meaning that an element of X star is a bounded linear operator from X into R. And all the results that we know about this apply to X star. So that's the dual of a given space, X. So if you are given X as a norm space, if you want to define the dual, you take the space of all linear bounded mapping or map from that X to R. We call it X star. So in other words, any bounded, any norm space X, that's a dual. That's a dual. Because we are talking about continuous, right? We have continuous. So we have because they are continuous, right? Element of these are continuous functional on X. Of course, functional is when the range is in R. We call it functional. Instead of calling bounded linear mapping, just the mapping we say functional, just to indicate that Y is equal to X, to R, Y equal to R. Then we call our bounded linear operator bounded linear functional. Yeah, the definition is even given here. A linear mapping F from a norm space X to R is called functional on X. Right? Now, if it is continuous, then you will say it's a continuous functional. Continuous function on X. So that's the definition of a dual. And we know already that for a dual, the norm on X star is the operator norm, right? Which is given by this. And we know also that it is the mean of C such that, as we know, this same norm is the mean or the infimum if you want. The infimum, they are all, we know that there are many equivalent definitions. They still hold. So it's the infimum of all constants C, of course C positive, such that absolute value, because we are in the range of f of x less than or equal to C norm of x. Right. So this is the infimum of us all such C is given by the norm of f, which you can use this way, or you can use this definition, or you can use the definition of the supremum where the norm of x is equal to 1 or less than or equal to 1. So all those norms are, in fact, those definitions define the same norm. All right. So now you see that here, instead of having the norm, we replace the norm with the absolute value because y is equal to x, y is equal to r, real numbers, and we know that in R, our norm is the absolute value. Right. So that is it for continuous functional. This will be the operator norm because f here is an operator. Right? It's an operator. And x star is a Banach space already because R is a Banach space. So that's a non-result. Right. Now this is what we call, because we are talking about dual, instead of writing f of x, when we are dealing with dual, instead of writing f of x, it will be better to denote f of x as f with x like this, just to indicate that this is a duality bracket. Because I take this lowercase f x is an element of capital X, and this f is in the dual. So if instead of writing f of x, we will be using the duality bracket to indicate that f is in the dual of x. Right. Of course, if I have a continuous function, for instance, if I have f, for instance, here, we have no problem to write this f of x, because f is a continuous function and it's continuous where? On the interval AB. You see, but f is not in the dual of the interval AB, right? If this C, whatsoever the space in which f is, where the dual of, for instance, the interval AB, then we could have written that. That's just to differentiate and to make the difference between f of x in the normal or ordinary way we write, or the usual way, and this new notation where f and its argument are in dual spaces, because I have x a space and x star the dual. You see that f now is the dual in the dual of its argument. So instead of writing f of x, we write it this way to indicate that the function and the argument are in dual spaces. That's the only difference. So it should not create a confusion, but I hope that with this one you will better understand that it's really good to make that difference. All right, so once you understand that, instead of writing f of x, when we have a function and its argument, and the function being in the dual of the space in which the argument is, instead of writing f of x, it's better to write the duality bracket f comma x with a duality bracket. That's what we'll be doing henceforth when we are in that scenario. Hahn-Banach Theorem and its corollary. So we will not spend that too much time on the Hahn-Banach Theorem. I will not spend too much time here because the most important thing to understand will be the weak topology where we are heading to. But it's good at least to state the theorem. That's what we'll do here. We state, and if you recall in the previous lecture, I mentioned this fact about the Hahn-Banach, where you have a function that is defined a function is defined on, let's say, on a set A, and you want to extend it. You want to extend it, or to, in fact, when you say extension, yeah, extension, in such a way that the original and its extension have the same norm. If you recall, I mentioned that previously, and I mentioned the Hahn-Banach theorem. Right. So in the Hahn-Banach theorem is similar, but there's a slight difference. So let's look at the theorem, at the statement of the theorem. So we have X. Let capital X be a real linear space, and we have F from that linear space X into R plus, and we assume that this phi is a semi-norm. Remember that the difference between a semi-norm and a norm is the property about being definite. In the semi-norm, you don't have the definiteness. You don't necessarily have the definiteness, meaning that if I have phi x equal to 0, I don't necessarily have x equal to 0. But if I compute phi of 0 is 0. But if it's definite, if it's definite, or if it's a norm, then phi x equal to 0 is equivalent to x is 0, right? That's the difference, the main difference between and a semi-norm. So in this case, we assume that phi is a semi-norm. Now we have this inequality between, okay, so we continue. Beside, now we have F, L, a subset of this. L, a subset of X. And we have L from the subspace into R. So we have L from R, which is a subspace, we assume that strictly included, into R plus, right? Or R plus or R. Oh. All right, that's just it. Okay, let me see if I can get rid of that. Okay. So we have L from here to there, and we also have phi. And we have this inequality between L and phi. So we have that L is less than or equal to, in terms of, if you could talk about the curve here, we say that the curve of F is below the curve of phi, right? If we could use that term in this case, and that is true for any X in L, right here. So that is true for any X in L. Now we want to extend this. That is, we want to define this L, lowercase l, which is defined on capital L. We want to extend it to the entire space capital L. Because remember that this lowercase l is only defined on capital L, which is not the entire space. It's just on the subspace. Now we want to extend it. We call that extension, right? We want to define it on the entire space. Right, we want to extend. Now, this extension will be made possible through this theorem, which is called Hahn-Banach Theorem. So, Hahn-Banach Theorem, actually, the takeaway here is that Hahn-Banach Theorem gives us an existence. So, it's an existent theorem. If I'm in this condition, it tells me if I want to use it, I will not need to prove it. If I use the theorem, now when you use the theorem, you don't need to prove the theorem. You use it to resolve. So this theorem tells me that if I have a function that is less than or equal to a seminorm on a subspace of a vector space, we can always extend it to the entire space to a new function, which we will call, you see, it's called here gamma, is it gamma? Lambda, capital lambda, you can see here, on the entire space, and it will still be below, or it will still be less than the seminorm. So this inequality will be maintained, and the two, because it's a linear functional, right? Both are linear functional. I can extend it, and now the norm of lowercase l and lambda will be the same. You will now have a larger norm. The norm of the two will be the same. That's the Hahn-Banach theorem. Or we also call it the separation theorem, right? Because this phi, in fact, it's as if I'm in a space like this, and then I have this phi, and the L is below here. It's a separation theorem. But I encourage you to look at the prescribed textbook because it's more, you have a more graphical, I don't know if it's in the prescribed textbook or in other textbooks, you have some schematic to represent the situation. Right. Okay, so that is it. Now, to say that this gamma is an extension, it means that gamma and L coincide on capital L, right? For any x in L, the two coincide, right? That's what it means to be extension. Extension means that we are the same on the smallest set. That is, if I restrict lambda to capital L, it will be equal to lowercase l. Right. Okay, and over all the entire space, you can see that we still have no. This is a typo. It should be phi. Right? We still have this. It will still be less. Right? It will still be less than phi. So this should be phi, please. This is phi. Eh? Instead of, it's still phi there. All right. So that inequality, because if I extend, the inequalities should be maintained. Right? The equality should be maintained. Why is it not L? It's not L because L is not defined on the entire space. L, according to our definition here, L is not only on lowercase l. It is phi that is defined on the entire space. You can see from here, phi is different from capital X. So if we extend, right, it makes sense that phi is still defined because it's defined for any x. But I cannot put L because I don't know L on X. I only know L on lowercase, on capital X. Right. So this is phi. Please change it. Right. Okay. So that is it. So that is it for Hahn-Banach theorem, and then the corollaries of that will be similar result, but in a different setting. Okay. Now, Okay, I said something. I am sorry. I said something that is not in the theorem, but in the corollary. It was about the equality between the norms. Okay, here in the original Hahn-Banach, is in the corollary. Sorry for that. It is in the corollaries that we'll be talking about the norm, because here our space X is not a norm space. It's just a vector space. Because here, if you look at the assumption, we say X a linear space. We did not mention norm. It's phi that is a semi-norm. Phi is a semi-norm, but not in X we don't have a norm. So far we don't have a norm. Even in if there's no norm in X, even in capital L, there's no norm, right? So when there will be norms, that's why we call it corollaries. Now, when we bring to the theorem, if we append extra condition, we call that corollaries. And that's what we will be looking at next. So corollary 245, given a real norm, linear space capital X. Now you see now it is norm. Now we put a norm in X. There's a norm. And we still have capital L, a subspace of L, right? And L, a bounded linear functional. Now we are saying that lowercase l is continuous. If it's continuous, it means that in L, capital L, we also have a norm. Of course, it can be the induced norm, because in L already, in capital X, we have a norm. Capital L being a subspace of capital X, you can induce the norm there, and it's bounded. So lowercase l is also a linear bounded functional. So we have exactly the same result as we have here, right? And the extra information now is that the norm or the operator norm of capital L and the operator norm of gamma are the same, right? They are the same. That's the difference. You see, we said without increasing the norm, so the norm remains the same. Okay. Okay, so that is it for this corollary. And the next corollary is X is a norm, linear spirit, also meaning that there's a norm there again. And X is a non-zero vector. Then there exists a continuous functional f into the job of capital X such that the operator norm of X of f is 1 and f of X is the norm of X. Remember what this means, right? Because f is in the dual of X, so instead of writing f of X, we write the duality bracket. Corollary meaning that in the proof we will use the Hahn-Banach theorem, right? Okay, so I will not go to the proof. As you can see here, we use the Hahn-Banach theorem. We construct using the Hahn-Banach theorem. I will not go through the proof. And this is another corollary with this result. And the proof is given, please. I encourage you to read. And we have the last corollary here, which I will not completely go through. So the next thing that we will cover will be the weak topology, and I will keep it for when? For next time. It might be tomorrow. Let me check how far, for how long have we been recording. Oh, less than 30 minutes, just 24, 25 minutes. Okay, so I encourage you to read the Hahn-Banach Theorem. You don't need to know the proof of the corollaries. You can just read through, but you don't need to know the proof. Okay, now to prepare the stage for the weak topology, I will take you back, if you recall, when we talked about, what was that? And I told you that this will come back to this. Remember when we talked about the topology, when we had a family of function, right? We define a topology for which that family of function will be continuous. So if you recall, that was after topology. Topology by open sets. Oh, it's not here. Wait. Oh, okay. Num space. All right. Okay. Well, let me see if no, but it's not that if I can find it is somewhere. It would be good. Okay, this is with topology. Oh, just a few pages. Okay, so let's tackle that. And on Friday, we'll meet on Friday, and that will be mainly tutorial. Okay, so we are going to tackle the weak topology, but we will do that I want to do that in a certain setting that will allow you to better understand, right? And for that, I want to connect it with what we did before. I want to connect that when we define initial topology. After topology, we encounter the concept of initial topology. That's how we call it. Call that initial topology. And if you recall, in the initial topology, what we did, we had let me share a new slide. So that I can easily recall the concept of initial topology. Okay, so of course, for the job, we know already that X norm linear space. Great. This we know. Now, the next thing we are going to talk about with topology. Okay, now the good thing with this, when you have a norm space, you have the first topology, which is called the strong topology, right? The topology defined by, because it's a norm space, right? X being a norm space, say we have X and its norm. I can just write norm like this, or I can put X there, right? It doesn't matter. Now, these norms define a topology. Because it's a metric space, right? And we know that if I have a metric space, I can always define the underlying topology, right, of a metric space. I just define the balls, right? I just define the balls, and then with those balls, I use open balls, and with that I can generate topology through open sets. And now this is what we call strong topology, the one that is defined from the norm, or the metric that the norm will define, because from a norm I can define a metric, right? The metric space has an underlying topology. That is our strong topology, right? So this topology is called the strong topology. Of course, when you say strong topology is in contrast with this weak topology, because now in the context of weak topology, there's a different approach, right? So I will just put it here that this is the strong topology. In contrast to weak topology. Now, for the weak topology, if you recall initial topology, so in the context of initial topology, if you recall, in the context of initial topology, we had, sorry, we had two topological spaces, X and Y sub X. when I say we have a first topology, and then we have a family of topological spaces. And from that, we define a family of mappings, right? So we have X, topological space, and we have Y sub I, a family of topological spaces. A family of topological spaces. So this was even before the notion of norm, if you call. That was the very beginning. And then we define calligraphic F to be this family F sub I defined from X into Y sub I. You agree with me that the fact that we have Y with a subscript, you understand that we fix our X, and then the range or the target space there will vary. So we take that family. So I in capital I, the set of indices. Obviously, I, the set of indices, is not necessarily finite. It's not necessarily finite. It's not necessarily countable. It's not necessarily countable. It's arbitrary. It can be anything. It's arbitrary. It can be uncountable. It can be countable. It can be anything. If you want it to be countable, we just take n. All right, so that is it for this. So this, you can see that this F is a family of mapping. The family of mapping, and each mapping is defined from X to Y. Right. Now, how did we define the initial topology? We define the initial topology as the topology for which each Fi is continuous. What's that? Yes, 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 yes. That's how we define. Because that was the question. Family of mappings. Right? So The weakest topology on X that makes every f sub I continuous is called the initial topology. And it is denoted sigma X with the family here, right? Of course, you can replace this F with this family, right? You might remove F and put this curly bracket with the Fi inside. So this is exactly the same thing. So that's how we define the initial topology. Good. So that is the recall. Now, what did we say here? We said the weakest topology on X. Weakest. Weakest, weak. You see the name weak again comes here. And weak, if you remember what we say by weak, it just means that the smallest topology. Because remember, if you have two topology, T1 and T2, if we have this, we say that T1 is weakest, it is weaker than T2, weaker. Is weaker. Meaning that all the open sets here are there. And this one is larger or is stronger than this one. So T1 is weaker than T2 or T2 is stronger than T1. And to be stronger means that I have more open sets. And here I have less open sets. But its open sets are also there. Right? So that is the weakest topology, the topology with less open sets. Okay, so that's what we call, that's why we say it's weak. It doesn't have enough. Weak. The number of opens is smaller compared to the other one. Okay. So this will be the weakest or the smallest possible topology, such as this, all the Fi will be continuous. So you see that that topology has very few open sets compared to the rest. Right. So okay, now that was a recall about initial topology. Now if you come back to weak topology, for a given norm space. Here, these are not necessarily norm spaces. They are just topological spaces. Right? In the sense of topology, you don't have norms here, just topology. Okay. Now you see that here we have X, which is a topological space. And now here we have mappings. Mappings, or in other words, here, the collection of F here, this family, it's a collection of mapping from this X to the Y sub i's. Now we are going to apply this concept to this norm space X. We have the norm space X, which has its topology defined by the norm. Now we want to define a new topology on this X, the weak topology, and that weak topology will exactly define it like this. You will see we will use exactly the same symbol, sigma, but sigma now we will call it sigma X like this and X star. This is how we will call our weak topology, which is a kind of initial topology on this. But we need to define this family because we don't have this family yet. And this family F will be this X star. Because remember, what is X star? It's a family, right, of mappings. Remember, this is a family of mapping. F is a family of mapping. X star is also a family of mappings. Let's go back to the definition here. If you recall the definition of our X star, we said that X star was what? Is the family of continuous mapping defined from X into R. So if we take all, and now you see that in our definition here, this I is in capital R, where we say capital I is just an arbitrary set. Arbitrary set. It's not countable, it's just arbitrary. So we can do the same thing here. If we look at our X star, if we take F equal to X star itself, we take X star to be our F, right? Which is this. So you see that here you have infinitely many. And how do you write this? All possible functions that you can imagine from X to R continuous. That's our F. Infinitely many. So that is our I there is infinitely many. It's a set. The subscript, we cannot even, that's just to count. When you put the subscript there, is to try to count the number of such. But here you have infinitely many. No one knows. It's infinitely many. You can consider as many as you want. So that is it. So that is the connection between initial topology and weak topology. So a weak topology is nothing else than the initial topology or a linear space, a non-linear space, where your family F is taken to be X star. So that is it. So that's the connection. Now we are going to see how to define the actual topology. Now that you understand what it means, so that was the first step to understand what it means. And then we can now dive into the nodes. Once we have set the stage, we can proceed. Okay, so let me great. Okay, so this being said, now we can go back to our node. The weak topology has fewer open sets because we saw that with the initial topology, you take the one that is the weakest, that is less open set, so fewer open set. Compare the topology induced by the norm, right? That is, we have X with this norm, that is the topology. It's a topological space. Right. Now, we take the weakest topology that will keep those mapping continuous. So we also recall that, yeah, X is a norm space, therefore it's a Hausdorff. Then X with the weak topology, this is how you should read it because this is a weak topology, is Hausdorff, no problem. Okay. Now, how do we define convergence in the weak topology? So if we have a sequence of element of capital X, that is capital X as a topological space, it has two topology. You have the norm. We know already how to write convergence of a sequence with the norm. We know that. Now, how do we write convergence when we have a weak topology? So that is it. We say that X converges weakly to X. Now, you see the notation. For normal convergence, we say Xn converges, we have full arrow to X or X0. That's full arrow. Now, this is strong convergence, right? Strong convergence. That is convergence from the strong topology. And now, if it converges weakly, we have only the arrow with one head. You see? That is weak convergence. Like this. One head. Instead of having the double head or the full head, double or full head, you have half to indicate weak convergence. All right. So that's a new notation. You should take note of that. So converges weakly to X if Xn converges to X in the weak topology. We already recall that initial topology are equivalent. Right? For F in the dual of capital X, right? F that is the image of the sequence converges to F is equivalent to X converges to X in the weak topology. So this is the definition. In other words, what does that mean? To write this convergence, because that's what we say here, is equivalent to this, because we say there's two statements are equivalent. So this convergence, that is this one, is equivalent to, for any F, remember that F is in the dual. So if I want to write the image of F of xn by F, I will write like this. And I will say it converges to Fx like this, when of course n goes to infinity. So this is how you write convergence in the weak topology. So that is true for any F in this. Because if you recall from the initial topology, our F was this. And now, if we use this topology, I mean this initial topology, calligraphic F, and we want to write exactly the same thing, we will say that for any I here, that is for F sub I of xn, or like this. Obviously, this F is not in the dual, so that's why we don't actually need the duality bracket. So we can just write Fi like this. Xn converges to Fi of x for any I. So this is how we are supposed to write in the initial topology for any I. For any I in capital I is equivalent to for any F in capital F. We have this with the duality bracket. And here we have exactly the same here. So this is for the initial topology, and this is for the weak topology. So that's convergence. Okay, so I can erase this or delete. Less messy. Okay, I can leave this one. Another definition. The convergence in the topology defined by the norm. Oh, I already told it. I mentioned this already. It's called a strong convergence. Right? Yeah, I indicated it here when I mentioned strong convergence with convergence. Right. Okay, so for the strong convergence, this is how you write it. When you say that xn converges to x for the topology for the norm of x, this is exactly what you write, because when you write convergence, you take this minus x for that norm less than epsilon, right? So which means that this norm converges to 0. Okay, so that's exactly the same thing. To say it's less than epsilon means that this norm converges to 0. I mentioned it in one of the classes, in one of the previous classes, and which is equivalent to this with the full arrow. That's strong convergence, or converges strongly. So this is what you know, and this is new. You see that here we use the duality bracket. Okay. Now, this is a good remark here. Since there are fewer open sets in the weak topology, if a sequence converges strongly in X, then it will also converge weakly in X. Because remember that the opens for the weak topology are also in the are part of the opens of the strong topologies, just that there are very few. So stronger implies, so you remember we say if we have a property for a strong topology, it will imply that it's true for the weak topology. That's exactly what we have here. If it converges for the strong topology, it will also converge for the weak. But if it converges for the weak topology, that's not necessarily true for the strong topology because it has few. So the open that you use to prove convergence here are very few to imply for the stronger topology. Okay, the weak limit is unique. Why? Because we saw that the weak topology is Hausdorff, right? It comes from the fact that it's Hausdorff. We mentioned it here. When you have a Hausdorff space, in a Hausdorff space, the limit will always be unique. It comes from there. So the weak limit is unique. If xn converges strongly to x, right? Of course, it's written here. You can see it from the arrow. Then it will converge weakly. The converse is false in general. So that's what we already mentioned above. And another, if xn converges weakly to x, then xn is bounded. We know that is true for the strong topology, or it's also true for the weak topology. That this is the meaning of the boundedness. So we have this, and the norm of x, that is the limit, is less than or equal to the limit inferior of the norm of xn. Limit inferior, you know already what it is. We covered that in the beginning when we talked about limit inferior. We did something on that limit inferior. In the slide, please check the slide. I think I emailed the slide to you. Anyway, it's in the notes. Limit inferior. Of course, it's even we define the limit inferior here. Where limit inferior of this is given by eta. Obviously, because we are taking a norm here, there should also be the norm. There should also be norm here. There should be norm here. We have the limit there, and we take the infimum of this set where m is greater than n. No? Because of this norm. If I remove the norm, then I don't need the norm inside. So I also need the norm inside. Ooh, really messy. So what I would do, I would just indicate that this is actually norm. Okay. Okay, another result. To say that xn converges to x0 weakly is equivalent to the modulus of xn is bounded, and for any, because we saw that for any, for convergence, remember convergence, we have for any f in x star in the duality, of course, it's because we break it into two, that now it will be in E, where E is dense in x star. Right? That's the difference. Right? Weak convergence just means that you have this one for any f in x star. Now, if we want to take it for any f not in x star but in a dense subset of x star, then we will need to add this one on top. Because, right? You see that here, we say that this weak convergence is equivalent to this for any x in x star. Now here you see that we are not saying for any x in x star, but in E, where E is dense in x star. You see? So this and this is not the same. We say for any x in E instead of x star. Now for that to remain equivalent, we need this second condition where we say the modulus of xn is bounded. So we need the two conditions for the equivalence. And finally, if xn converges strongly towards x0, and if fn, you see here, xn are elements of x, right? This xn belong to x, capital X, and these ones belong to the dual, right? So we have xn in x converging strongly to x0, and fn in x star converging strongly to f, right? And strong convergence, this is what it means. Then, if we take the couple, that is fn of xn will converge to f of x. Because there is the duality, that's why we use the duality brackets. Okay, so this ends okay, so that is it for that corollary. And we have another one and the proof. So I will not go to the proof. You can read it yourself. So the last theorem is this one. In a finite dimensional space, remember that we have been dealing with infinite dimensional spaces. And in general, in linear, in functional analysis, the spaces we are dealing with are, in general, infinite dimensional spaces. Now, if X is finite dimensional space, then the concept of weak and strong convergence are the same, right? So, finite dimensional space, norm space. So, we are told that Xn converges weakly to X0 in X. That's for the weak topology. Then, it will converge for the strong topology. In other words, in a finite dimensional space, strong and weak convergence are similar. That is just to round up, right? To wrap up. In an infinite dimensional space, we saw that the converse is not true. If we converge for the weak topology, we will not converge for the strong topology. Not necessarily. But if we are in a finite dimensional space, the two are equivalent. You know already that strong topology will imply weak topology, but here we have the converse, that is weak topology implies strong topology. So the two are equivalent. That is only true in a finite dimensional space, which I need to box. I'll put in a frame here. It's only true due to this fact. And for the proof, you have the proof here right beside your eyes, which I encourage you to try to read and understand. We will meet on Friday, where we will discuss all this in detail. Please read, and make sure you are well prepared for Friday so that you can go through the tutorial, discuss the concept and everything. Thank you so much for your time, the time that you will take to read, obviously. And I wish you all the best. I wish you to enjoy this concept, which is really nice. It will not appear easy In the first sight, you have to read again until it sinks into your brain. God bless you and see you during the tutorial. Bye-bye.